Welcome back to A-Star Science, part of our GCSE Must Know Chemistry series. Today we're going to talk about a topic that some people find difficult, some students find difficult. In fact, students seem to find this topic of quantitative chemistry the most difficult, along with other topics like electrolysis, when they're doing their chemistry GCSE, and even in A level, this topic can be somewhat difficult. But it's very important because in chemistry, quantitative chemistry, meaning determining the amounts of substance, this particular concept of Avogardo's constant and the mole is the most important topic that you need to understand to do these questions correctly. So let's jump right in. Avogardo's constant, well, what is it? First of all, Avogardo's constant is just a number which relates to the number of units that we use in chemistry. And we call that 1 mole. Mole is short for molecule. So in any 1 mole of a substance, you will have this many units, which we call Avogadro's constant, in that substance. That could include the number of atoms. It could include the number of molecules. It could include the number of ions. It doesn't matter. As long as you have 1 mole of that substance, you have this many units of that particular label or particular variable that you're discussing, whether it's atoms, molecules, or ions. It's similar to when people use the term 1 dozen. We know that 1 dozen equals 12 units of something. That could be 12 dozen pencils. It could be 1 dozen, 1 dozen would equal 12 pencils. 1 dozen would equal 12 cars. If you had 1 dozen mountains, it doesn't matter, that would be 12 mountains. And it's the same thing in chemistry, that the unit of 1 mole would equal 6.02 times 10 to the 23rd of the number of those particular units: atoms, molecules, ions, so on and so on. So let's see how we use that. Well, in order to understand that, we need to understand how do we calculate moles. So as a quick refresher, we know that the number of moles of something is found by the mass of that particular substance in grams over its atomic mass or molecular mass, what we call MR. Okay? So in effect, 1 mole of a substance is equal to its mass in grams. And we know that in 1 mole, we have 6.02 times 10 to the 10 to the 23rd of these units. So for example, if we had 1 mole of, let's say, lithium, on the periodic table, lithium has an atomic mass of 7. So we would need 7 grams of lithium to have 1 mole. And that would have how many lithium atoms? Well, 6.02 times 10 to the 23rd lithium atoms in it. If we had, for example, 1 mole of chlorine, well, chlorine, we know that on the periodic table, its MR, its AR is 35.5. We would need 35 grams of that, and we would have 6.02 times 10 to the 23rd chlorine atoms in that particular 1 mole, or chlorine molecules in this case. So how about for other substances? Let's say we had 1 mole of water, which is H2O. Well, water's MR is 2 for hydrogen, because it's 1 times 2, plus 16 for oxygen, which equals 18. So we would need 18 grams of water for 1 mole. And of course, that means we would have 6.02 times 10 to the 23rd molecules of water in that 18 grams. So we see 1 mole is always equal to this number, 6.02 times 10 to the 23rd of a particular substance. Now, we can use this as well when we're looking at formulas. So if I'm looking, for example, at H2O, this also tells me that for every water molecule, I have 2 moles of hydrogen to every 1 mole of oxygen. And I want you to start thinking about formulas that way. Let's say we looked at iron oxide, Fe2O3. This is telling us that for every 2 moles of iron, we need 3 moles of oxygen. This same understanding can be applied also to chemical equations for chemical reactions. So let's look at a simple equation for this. If we take hydrogen plus oxygen and react that to make water, and then we balance it, which means we need 2 oxygens on the right, so I'll put a 2 here. That means we need 4 oxygens on the left. This is telling us that it takes 2 hydrogen molecules for every 1 oxygen molecule to produce 2 water molecules. Now remember, we said moles are short for molecules. So this is in effect telling us that we need 2 moles of hydrogen for every 1 mole of oxygen in order to produce 2 moles of water. So this is really important for doing quantitative chemistry, because if we know the moles of one, for example, if we know the moles of hydrogen, we could then determine the moles of oxygen needed, because it's a 2-to-1 ratio. And that's how we do our calculations in chemistry for quantitative chemistry. If you're not sure about that, please look at my video on limiting reactants and amounts of substance, as well as titrations, which helps with that particular topic more. Now, let's do a quick example of this. If we take a look, for example, at water, which is H2O, we know from what we said previously that the MR of water is 18. That's the MR, which is the relative molecular mass. That means we need 18 grams of water to equal 1 mole. That means in that 1 mole, there's going to be 6.02 times 10 to the 23rd water molecules. And we know water molecules are H2O. Now, what does that tell us about the number of hydrogens and oxygens in 1 mole of water? Well, the number of oxygen would equal 6.02 times 10 to the 23rd, because that's how many water molecules it is. But the number of hydrogen, let's just put oxygen next to this one, oxygen atoms, the number of hydrogen atoms would be times 2, because as we can see, hydrogen is 2 to 1 to oxygen. So that means we need 2 times 6.02 times 10 to the 23rd to calculate the number of hydrogen atoms in every water molecule, which is 1.204 times 10 to the 24. So this is Avogadro's constant and the mole and how it relates. And what's really interesting is that Avogadro's constant not only is just an arbitrary number, it's a number that's actually been proven through science, through looking at the electron density and measuring charge. And if you want more information about that, definitely go and research it, because it's really amazing how they were able to get down to the exact number of Avogadro's constant, which, as a point of fact, is actually much longer than 6.02. It has several digits after the decimal point. But for GCSE, they are fine with you using it to 2 numbers after the decimal point. This is A-Star Science, GCSE Must Know Chemistry. Please like the video, subscribe, leave a comment below for any video that you would like me to do, any topics that you may struggle with in your GCSE chemistry.